Hi, welcome back to this video series on Diffie-Hellman key exchange, and in particular, the Diffie-Hellman parameter setup. I have been talking about different characteristics of the DH parameter setup. Today, I wanted to talk about some loose ends that we haven't really talked about in the past. The purpose of this video is to clarify what type of information leakage happens when we use traditional DH algorithm as opposed to use the safe prime. Okay, so I quickly wanted to recall the traditional DH algorithm, of course. So we have our friends Alice and Bob. Alice will pick a random number x. She will compute g power x mod p. And then she sends that to Bob. Bob does something symmetric on his side. As you can see on the slide, Bob picks a random y. He computes g power y mod p. Of course, they both agreed on g and p already before the protocol starts. Bob sends his public key b to Alice. And then Alice takes Bob's public key and mix it up with her private key in the same style. Bob will also do the same. Because of the properties of exponent, they both will arrive at the same key. That's basically the whole purpose of this DH key exchange algorithm is, or key agreement algorithm is. But the question now is that here we are using regular prime p as opposed to so-called safe primes. Let's assume this is just a regular prime, right? P can be, for example, 13. 13 is not a safe prime, right? It's not 2 times some other prime plus 1. Anyway, so in that case, the question is, what type of information leakage happens? Can Eve detect anything about X or Y? Okay, I will show you that there is some information leakage when we use the basic DH algorithm as you see on the slides here, okay? Before I get into that and discuss what type of information is leaked, I have to introduce to you something called quadratic residue. Okay, so let's get into the details of quadratic residue now. So the idea of quadratic residue is really interesting. If you recall, for example, in your traditional number theory, perfect squares, for example, like for example 16 is a perfect square because it can be written as something like this, right? 16 is equal to 4 power 2. Okay, but this is no modular arithmetic here. But the question is now in the context of modular arithmetic, for example, let's say p equal to 13, our clock that we have talked in the past, 13, right? Can we say 6 is a square or not? Can we write 6 as some number power 2? Can we write 6 is some number power 2? Of course, it's not possible to write 6 as a number of power 2 in regular integers, but in mod, sometimes it is possible. So in this case, the question is, can we do that? So I want you to think about it for a moment. The answer is yes, and I will show you on X shortly. This is the quadratic residue concept. Quadratic residue means given a number y, can you write that as power of 2? Essentially, that's basically it. You know, so 6, for example, is a quadratic residue because you can find an x, and x square will give you 6. Okay, in mod 13. Okay, so the idea is oh, I think I messed up. One moment, sorry. It's not 6. Sorry, it's 9. Okay, 9 is a quadratic residue. You could write 9 as power of a 3 square. Very easy, right? What about much more harder one like 10? Okay, can you write 10 as power of 2? In regular integers you can't, but in modular arithmetic you can write 10 as some number power 2. Okay, so let me quickly check that and show you how. For that, I have created a little program that will help us along the way. So before I get into the program details, let me just run this and tell you exactly. So let me work with the group 13, Z13, right? Okay. What you're seeing is a table of numbers, right? Each row is basically, first row is generated by G equal to 1, G equal to 2, G equal to 3 all the way up to G equal to 12, because these are the possible generators for the group, right? Possible. We don't know exactly, but I said 10 is a square number. We can easily confirm that, because, for example, if you take number 6, right? 6 square. What is 6 square? If you look at the second column now, 6 square is basically 10, right? So 10 has been written as 6 square, which makes sense. 6 square is 36. 36 mod 13 is 10. Okay, so 10 itself is a square number. On the other hand, number like 6, can we write 6 as a square number? Well, if you look at the second column here, the second column is 1, 4, 9, 3, 10, 12, right? Only those numbers. The second column is, we can actually cut it using, let me just do this way. Let me just copy this into a file, say q.txt, right? And cut the second column using awk, for example, awk print column 2. Let's see what happens. Okay, so we can even do more. We can just select the unique numbers. So the square numbers are 1, 10, 12, 3, 4, 9. 4, 9 is obvious. 4 is 2 square, 9 is 3 square. But interestingly, even 3 is a square number. We can write 3 as a square number. Now we can go back and run it again. Why do we say 3 is a square number? Because 4 square is 16. 16 mod 13 is 3. So we can find out easily a number is a square number or not, without even computing the square. That's the next part of the lecture now. Okay, anyway, so what you have seen so far is that some numbers are square numbers and some are not. And if you count the number of square numbers, you will see something interesting. Let's see, 1, 10, 12, 3. Okay, so it's how many? 6, right? If you remember Z13 as a multiplicative group has numbers from 1 to 12. So half of them are square numbers and half of them are not square numbers. So that's the first observation. Okay, so let's remember this now. For now, half of the numbers in Z13 is a square number. Okay, is a set of square numbers, and the remaining, of course, is not a square number, right? Okay. So, okay, one moment. Right. So, what is the next part? The next part is that we talked about generator on the slides. Let me go back to the slides. We talked about a bunch of generators during my other videos. Here we see 2 as a generator. The question is, the reason why 2 is generator is because it generates all the numbers of our set. What about other numbers? Can we have other numbers? We can look at it. 2 is a generator because it generates all of the numbers. 3 can't be a generator because it only generates first 3 numbers, right? 4, no, because it's only generates a few numbers before it gets a 1. The square numbers naturally cannot be a generator. See here, the generator. What are the generators we have? 2 is a generator, 6 is a generator, 7 is a generator because it generates all of the elements, and 11 is a generator. So the generators are different from the square numbers. The square numbers are like 1, 10, 12, 3, 4, 9. It must be clear now why, because if a square number was a generator, it would have only generated another square number, and we wouldn't have been able to generate all the numbers of our set. Okay, let me recall what I'm trying to say here. The generator that we pick to generate all the elements of the group have to be not a square number. If you're working with the traditional DH algorithm, where the prime P need not be a safe prime. In that case, the number that you're generating, the G, has to be a non-square number. That's the reason why we picked 2 other day when we generated it. We cannot pick, of course, 1 is useless because it will not generate anything. 10, 12, 3, 4, 9. These numbers cannot be picked as a good generator when you're working with a non-safe prime case. Okay. What about the information leakage part? The information leakage part is really interesting, actually. It turned out that if Eve computes something called quadratic residue, she can figure out whether the private key of Alice or Bob is actually an even number or not. So essentially, she can learn the least significant bit of the private number. So what I mean to say here is this, this one, the x, right? Of course, x itself is private, but g power x is public, right? G power x mod p is public. From capital A, Eve can figure out the least significant bit of x. I will show you how. Okay, so let's consider this example now. Okay, I need to show you an important theorem of Euler. Euler discovered this really important theorem that helps us to detect this information leakage problem. Okay, Euler's theorem. Euler has hundreds and hundreds of theorems, and one of the theorems is a really beautiful theorem he wrote. If you have an odd prime number, P be an odd prime number, usually in cryptography, our primes are all odd, and we never have P equal to 2, very rarely. So I will not say odd, but let's say prime P, right? If you wanted to check whether a number is a quadratic residue or not, for example, 10 was a quadratic residue, right? We were able to write 10 as a power of some number power 2, right? But without finding the actual x, in this case, for example, 10 is x power 2. If you find x, you know 10 must be a quadratic residue. But Euler has a beautiful idea. He said like this: if P is a prime, then a number A is a quadratic residue, if and only if A power P minus 1 by 2, the P minus 1 by 2 is an exponent, right? A power P minus 1 by 2 is congruent to 1 mod P, okay? If this condition is violated, then we can say A cannot be a quadratic residue. So we can use this theorem now to reason about whether we can find out the least significant bit of the private keys, okay? So let me show you how. Let's consider this case. For example, G being 7, okay? Is 7 a good generator? Yes, it generates all the elements of our group. So 7 is a good generator, okay? Let me pick G to be 7. Let me pick my G to be 7. Okay, so what am I going to do now? G is 7. Let's assume I am Alice for now, and I picked my x, the private x, right? Private x as 4, okay? Of course, 4 is secret, nobody knows except Alice. But can Eve figure out that my x is an even number? Can Eve find out x is even number? Here is how we can go about. What is Eve seeing from Bob? From Alice? Alice will send G power 4, right? Which is equal to 7 power 4. 7 power 4, if you look at my table here, 7 power 4 is 9, right? 9 in mod 13, right? We are working with P being 13. Okay, so 7 power 4 is same as 9 in P in 13 group, okay? So now question is, can we now use the Euler's theorem to detect whether 9 is what the public key 9 is a quadratic residue or not? Is 9 a quadratic residue? Okay, so A is 9. Now I'm going to apply Euler's theorem. Is A equal to 9 quadratic residue? Okay, how do I check that? All I'm going to do is I'm going to compute A power P minus 1 by 2. Okay, so I plug in the numbers, so it will be 9 power 13 minus 1 is 12. 12 by 2 is 6. Okay, 9 power 6 mod 13 is what I'm working with. So we can find out 9 power 6 easily from my table here. What is 9 power 6? Which is nothing but 1, because this is where you're seeing 1. So text. Okay, so this is nothing but 1. Okay, so the Euler's Criterion theorem says a number is a quadratic residue only if A power P minus 1 by 2 is 1, which is true. Therefore, Alice can conclude, well, Alice already can know it is her private key. Therefore, Eve can conclude x must be even, which is true because we saw x is equal to 4. That's what Alice picked. Okay. All right. What about another case? Let's consider the case where next round. Let's do the next round. Okay. Let's do the next round now. The next round, let's pick another number. Let's say Alice picked the number to be say 5. Okay, so G is still 7. Her private X is well, P is still 13. We are still in the same group. Let's say her private X is 5, which is odd. Can we figure out that? Okay, what is G power X, which is nothing but 7 power 5, which is nothing but in mod 13. 7 power 5 is what is 7 power 5? We are in 7. 7 power 5 is 11. Okay, so 11 in mod 13. Okay, but can we now figure out whether 11 is a quadratic residue? Is it a quadratic residue or not? Now we do a power p minus 1 by 2, which is 11 power 6, which is what is 11 power 6 in mod 13? 11 power 6 is 12. Of course, 12 is not equal to 1. Therefore, we can conclude that X is well, A is not a quadratic residue. Therefore, what we can say is that how did we get this A equal to 11? A is nothing but G power X. Therefore, we can conclude X must be odd. So, what you're seeing here is that with the help of quadratic residue, Eve can determine the least significant bit. What is the information leakage? Information leakage is just a little bit information, of course. The least significant bit of private keys are leaked. Okay, very simple. All Eve has to do is apply Euler's theorem. Apply Euler's theorem to compute the whatever I said here is called the Legendre symbol, by the way. Anyway, that's not necessary at this point. Apply Euler's theorem to compute a power p minus 1 by 2, right? If this is true, then we know if this is 1 in mod p, we know A has to be a quadratic residue. That's basically what Euler proved. So we are using this Euler's theorem to detect the least significant bit. So again, what I'm trying to do is that I'm checking whether G power X is a square number or not. If it is a square number, I do know X is even. If it is not, X has to be odd, right? So that's basically the main point of using this quadratic residue technique to figure out the least significant bit. Okay, what if I use the safe prime? Let's say my primes are safe. Let's say instead of p equal to 13, my prime is 11. 11 is a safe prime because p is equal to 2 times q plus 1. We can find out quickly q must be 5. So in this case, can we not apply the same trick and find out the least significant bit? It turned out the answer is no, it's not possible. Okay, let me show you why. If you now run the same program again, let's do this quickly, right? On the cyclic group 11, which is a safe prime. Okay, now if you look at the second column has 1, 4, 3, 9, right? That's the second column of this table. That means the square numbers are, what are the square numbers now? The square numbers are just 1, 3, 4, 5, right? 1, 3, 4, 5, and 9. Okay, and of course there are 5 elements, and then the remaining 5 elements are non-square elements. These are square elements. Okay, and the remaining others are non-square elements. Okay, but what is the group generator in the case of a safe prime? Okay, in the case of a safe prime, we get into an interesting situation. The group generator has to be one of the square elements. Why? Because we talked about how do we select the group generator. The group generator is selected by taking some random number alpha from the group Z13 or Z11 in this case, and then we raise that to power 2. Okay, that means already we know G must be a square number. Okay, if G is a square number, all the elements G generates must also be a square number. Okay, so each and every element must be a square number. So the subgroup that we will work with, actually A is nothing but all the elements that are square elements. Okay, so the subgroup actually is made of 1, 3, 4, 5, 9 only. Okay, those are the subgroups that we will work with. And one thing is not correct here. This G equal to 7 cannot be G equal to 7 cannot be a generator, because G equal to 7 is not a square element. Okay. All right. So now let's think about how do we find out the least significant bit in the case of a safe prime. Can we do that? The answer is no. We can't. Okay. Why? As I said, all the elements that are generated by the group generator are square numbers. Okay, because as I said earlier, the generator can be one of the numbers, either 4, 9, 3, 5 in the case of the safe prime. Therefore, there is no notion of square and non-square, right? Eve is receiving only square numbers. So a generator can be, for example, let me do one exercise quickly, right? Let me select a random number alpha, be my alpha. What is my alpha? One moment. My alpha, let me take my alpha to be just 3 for a moment. Okay. So what is 3 power 2? Alpha square will be my generator. 3 square is 9, right? So my generator is 9, which is part of the square in the second column. So what if Alice selects her private x to be say 4? What is G power 4? Well, 9 power 4, right? G power x is equal to 9 power 4. What is 9 power 4? 9 power 4 is basically 5. From my table, we can see that in mod 11. Okay, so she's sending 5 to Bob, but now what can Eve do? Well, Eve takes the number 5, but she can't do much, because 5 is actually an even number, right? We can see 5 is an even number because it's part of the second column, right? You see the second column of my table that I generated. 5 is part of the even number list, so there is no point. Well, what if we change the x to be something more interesting? Let's say x to be say a non-number like 3. Okay, what is now G power x, which is a 9 power 3, right? What is 9 power 3? Again, we can go to the table and look at 9 power 3. 9 power 3 is basically 3, which is still an even number, because 3 is part of the second column. Okay, so it doesn't matter whether x is odd or even. The answer that Eve is observing, G power x, is always a square number. Therefore, Eve cannot learn the least significant bit, as far as we know, using this technique. Okay, when using safe primes. Okay, so to sum up the long story short, using safe primes actually hide the if we use the safe primes, what do we hide? We hide the least significant bit, because the public keys that are exchanged are always a square number. So Eve is not able to learn much about the private value. On the other hand, if it is a traditional prime, not necessarily safe prime, in that case, it is possible for Eve to learn the least significant bit. Okay, that's basically it. And one more thing, finally, before I wrap up, is that if we now go back quickly to the regular prime case, right? Let me run this 13 case. The square numbers, as I mentioned earlier, what are the square numbers? The square numbers are 1, 10, 12, 3, 4, 9, right? They can't be generators, right? For regular primes. On the other hand, the non-square numbers, what are the non-square numbers? 2, 5, 2, 5. For example, 5 is a non-square number, right? Because it's not part of the second column. But 5 cannot be a generator either, because it's only generating 5 elements or 4 elements, right? After 4 elements, it repeats. So not not all non-squares are actually generators. That's the important point I wanted to highlight. All right, that's basically the one of the loose ends I was thinking to cover for today, and thank you very much.